So distance, speed, acceleration and graphs, all these are tied up together in this little presentation. You've really got to know how to calculate speed, you've got to know how to calculate acceleration. You've got to know the properties of graphs like a distance time graph and a speed time graph. So okay, here we go. How is speed calculated? You need to know this formula. It's on the formula sheet. It's a very simple formula. You've been using it probably throughout school since year 8. Speed equals distance travelled divided by the time taken. So however far you go divided by however long it takes you to go that distance, divide distance by time and you get speed. In physics we measure distance in meters. Important, that will be on some questions to try and trick you. Always convert it to meters and convert the time to seconds, and then your speed will be measured in meters per seconds, and the units are m/s, which is meters per second. I know that we often talk about speed being in miles per hour or kilometers per hour, but in all the physics questions you'll get on the physics paper it is meters per second. Let's do a little example. If a train takes 100 seconds to travel 1,500 meters, what is the speed of the train? Quite simply, here's our formula. Speed equals distance divided by time. So we take the distance, 1,500 divided by 100, and you can either do that in your head or put it in a calculator, and you get a speed of 15 meters per second. Okay, if you like using the formula triangles, then this is what the formula triangle looks for the speed time. Distance equals speed times time, speed equals distance divided by time, or time equals distance divided by speed. How am I doing that? Well, you cover the quantity up. So to find speed, cover up s, and you're left with distance divided by time. If you wanted to find time or distance, cover those up and the formula triangle can help you. Remember, you're not given the formula triangles, but if you can remember them, they might help. Okay, let's look at a distance time graph. This is a graph plotted of a graph of distance, how far this thing has travelled, or car or person, against the time it took them. So you can see for the 60 seconds, whatever this thing, we started off and we've sort of moved up to 200 meters, 400 meters, 600, and we've got to 1,000 meters. If we look at the slopes or gradient, this is the most important thing to get from this graph. Then you can see that at this point, once the slope is curved, then our speed is increasing, but it's not increasing at a uniform rate. So it's changing differently too at this part of the graph. When you've got a straight graph, then this gradient is constant. So we say that this straight slope with a constant gradient, we're moving at a uniform speed, we're going at a constant speed. And here again, the slope means, the changing slope means that the speed is changing. And then when it's flat, if you think when it's flat, that means it's not moving. So a distance time flat graph is not moving. The biggest mistake is people say that that is a constant speed, but no, this is the constant speed section. This is when, if you want to really get into it, this is when the car or whatever it is accelerating, and this is when it's decelerating here. Okay, so lots of properties of a distance time graph, all linked to speed. The slope is the speed. On to acceleration. Acceleration is how much the speed of an object is increasing every second. So just think through that. This time it's not how the distance is changing with time, it's how the speed changes with time. So for example, if an object increases its speed by 5 meters per second every second, then it has an acceleration of 5 meters per second, and this is how we write that. We say it's 5 meters per second squared. Just like makes it a little bit easier to say and write rather than saying 5 meters per second. So in 1 second, its speed will have gone up from 0 to 5 meters per second. In the next second, its speed will go up from 5 to 10. In the next second, 5 to 15 meters per second, etc. This is the formula. Again, you're given it, but you need to know how to use it. The acceleration is the increase in speed divided by the time taken. And as I've said, our units are meters per second squared. Let's do a little example. A racing car accelerates from rest to a speed of 60 meters per second. in a time of 4 seconds. What is the acceleration of the car? Here's the formula. Acceleration is change in speed divided by time taken. So the tricky thing sometimes is to work out the change in speed. Now remember, we have gone from rest to 60. So the change is 0 to 60, which is 60. And that has taken us 4 seconds. So 60 divided by 4 will be our acceleration. If you need a calculator, punch it in and you get 15 meters per second squared. Don't forget the units. If you're a fan of the formula triangles, this is the acceleration formula triangle, where acceleration equals speed over time, or the change in speed over time, and exactly like before, you cover the unit that you want to find. So to find acceleration, you cover the A and you get S divided by T, or speed divided by time. If we look at a speed time graph, this time it's not a distance time graph, it's a speed time graph. We need to think about what the gradient or the slope of a speed time graph means. If you think about this part of the graph, our speed is increasing with time. So in the first 20 seconds, our speed goes from 0 up to about 28 meters per second. So we could work out an acceleration from that, couldn't we? We'll do some later, we'll do an example. So this is an increasing speed, this is an acceleration, but the fact that it's a straight line shows that it's a constant acceleration. This flat bit of the graph is when the car is moving at a constant speed. I can see that because at 20 seconds it's moving at about 27 meters per second, and it is at 25, 30 and 35 as well. The speed doesn't change. After 35 seconds our car seems to slow down, so the speed is decreasing from about 27 meters per second all the way down to 0. So this section of the graph, it's slowing down, or it's got a constant deceleration. We just put some labels on, that's just to confirm it. So the straight slope up, accelerating at a uniform, no slope or flat, speed is stationary, straight slope down, the object is decelerating. Okay, this is an interesting bit of a speed time graph. We can look at the area underneath the graph. Now the area underneath the graph is actually the distance travelled. So if you've got a speed time graph, if you calculate the area beneath, quite literally how many squares are underneath the graph, then that will tell you the distance travelled. If you think about why that is, then the formula for distance is speed times time. So if you multiply speed by time, then that's what this side of the graph is, speed, and that's what this side of the graph is, time. So if you go speed times time, you end up with an area. It's kind of like two sides of a square. If you imagine this is a square, this graph is a square. If you multiply speed by time, then the area of the square becomes the distance travelled. The only thing you need to be a little bit clever with is when you've got sloping sections where it's accelerating, then you need to think about the area of a triangle maybe. Have a look at this little example. We can split this graph into three areas, A, B and C. A is a triangle, B is a rectangle, C is a triangle. So if we first of all do area A, we've got to do this, got to treat this as a triangle and do its, and the area is half the base times the height. So half of 4 multiplied by 7. So half times 4 times 7 gives us an answer of 14, so that's 14 meters. If we then do area B, this is nice and easy, it's just a rectangle, so it's base times height. So remember, it's not 7, it's 4 to 7, so 1, 2, 3, and the height is 0 up to 7, so it's 3 times 7, which is 21 meters. And the final section, C, this is a triangle again, so we need to do half base times height. So 7 to 9, this is 2. So we've got half times 2 times 7, because this is the height here, which gives us an answer of 7 meters. And to get our final answer, we add up our three answers, 14 plus 21 plus 7. Shove that in your calculator, and you get a total distance travelled of 42 meters. So let's just put our graphs together. Now we've looked at speed time and distance time graph. If you are not moving, then these two graphs, the distance time first, this line is showing an object not moving because the distance is stopping the same. As time goes on, the distance doesn't change. This graph, a speed time graph, For not moving, the line's got to be at the bottom on zero speed here. Very often people will confuse this and say this is a constant speed, but it's not. A distance time graph, a flat line anywhere means not moving. For a speed time graph, it's a line across the zero, so across the bottom. Okay, if we look at something slowing down or decelerating, this is your distance time graph. If the curve is doing this, then it means there's less and less distance being travelled as time goes on, so it's slowing down. But a speed time graph, slowing down is a slope downwards because the speed is reducing. That's quite a difficult one to get your head around, maybe this one, but compare them, think about them, and you should be fine. Okay, if we look at speeding up, this is the speed time we're doing first. So the speed time, our speed is increasing. So as time goes on, the speed increases. So this is an object accelerating, but our distance time graph has to look like this because the rate that the distance is increasing is going up. So this is sloping upwards and getting steeper and steeper and steeper because the distance travelled in a time, in a particular time, so 1 second, is getting more and more and more. So both of these are accelerating. And finally, a constant speed. This is a constant speed for a speed time graph. If you imagine the speed here of this value, this was say 5 meters per second. It's always going 5 meters per second. As time goes on, it's going 5 meters per second. But on a distance time graph, a constant speed is a constant slope. So the distance is increasing with time, but it's going up at a constant rate. Every, say, 1 second, it's going up at the same rate. So you have a constant speed. Okay, if you just look at some examples, if you looked at this particular graph, it's a distance time graph. We could answer 4 questions. All the answers are up in case you're working through this and you want to pause the video. What is the speed during the first 20 seconds? So if we look in the first 20 seconds, we have done 10 meters. So speed is distance divided by time. So in the first 20 seconds, 10 divided by 20 gives you an answer of 0.5. Number 2, how far is the object from the start after 60 seconds? So if we look at 60 seconds and go and read across, then we know that we have travelled in total 40 meters. So we are 40 meters from the start after 60 seconds. What is the speed during the last 40 seconds? Well, the last 40 seconds is between 60 and 100. And in those 40 seconds, our distance goes from 40 all the way down to 0. So it travels 40 meters and it does that in 40 seconds. So speed equals distance divided by time. So it's the distance 40 divided by the time 40. It's actually 1 meters per second. And just to remind you, I'm saying we're going backwards, we're in reverse because we're coming back to where we started from. And finally, when was the object travelling at its fastest speed? Well, we need to look at the slope, and between 40 and 60 seconds, this slope is steeper than this slope. If you compare them, in 3 squares, I go up 3 squares in 1 square, whereas here I come down 4 squares in 2. So this actually looks steeper, it is a steeper slope. So I'm travelling fastest between 40 and 60. Okay, if we do an acceleration graph, if we look at the example here, what is the average speed in the first 10 seconds? So in the first 10 seconds, here we go, 10 seconds, we do we go from 0 to 40. So if we look at the average speed, well, the average speed is, we'd have to sort of say we start off at 0, we go to 40, so the average speed is 20 meters per second. It's sort of halfway between our starting and our final. I've done an average of 0 and 40, added them together and divided by 2 to get 20. What is the acceleration between 20 and 30? So if we look between 20 and 30, our speed has gone from 40 to 60. So using our formula, which is here, the increase in speed is 20 and the time taken is 10. So 20 divided by 10 gives us an answer of 2 meters per second squared. So our acceleration is 2 meters per second squared. What is the deceleration between 30 and 50? So we're slowing down on this section of the graph. So between 30 and 50 seconds, that's 20 seconds, we have gone from 60 down to 0. So our change in speed is a negative this time, or it's a decrease. Our decrease in speed is 60. We've done it in 20 seconds, so 60 divided by 20 gives an answer of 3 meters per second squared.